Good morning, everyone. Welcome to the class of CE261 Fluid Mechanics. So today we'll discuss. Let's start from steady incompressible flow in pressure conduits. So pressure conduits is basically what the pipe, mm, which carries the liquid. Steady incompressible flow in pressure conduits. So basically, we are dealing with the water flow through the pipe here. Laminar and turbulent flow. By now we know what is laminar flow and what is turbulent flow. So if we observe the flow phenomena in a pipe, let's say this is a pipe and water is flowing through this pipe. Okay, and you know that as the water flows with a particular velocity, then there is friction, shear stress generation between the surface of the wall and different layers of the water, which actually induce the frictional head loss. Hmm. Now if we observe how this head loss changes with the velocity, we will see this. Can you see this plot, guys?
Yes, sir.
Let's say you have velocity here and head loss here. So for a particular velocity 10, you have a head loss 2, let's say. For 15, you have 3, and so on. If you plot this, you'll see that you're initially you're getting a straight line, but up to certain point, you'll see that the curve is moving like this. This is no more a linear line. Okay. Now, if you go
Yes, sir.
back, you'll see it's going backward in this direction. So basically, this is this. Then I'm talking about this. Then B to C, this, and then if you go backward, then C to B, C to A. I'm sorry, this is A, C to A. Okay, so what's happening here? This is basically HF here, this head loss, or HL, whatever you say, and this is the velocity here. If you increase the velocity, head loss will increase like this, and then after a certain point here, it will no more be a linear one. It will be a curved. Are you following me, guys?
Yes, sir. Yes, sir.
Yes, sir.
So as you can see, these 2 points A and C, we can divide we can divide this in terms of this different behavior characteristic of this graph. So here, up to this part, the flow was laminar, and beyond the point C, the flow was turbulent. As you know that in turbulent flow, the velocity is much higher. As you can see, yes, the velocity is higher in turbulent region. So this is laminar, this is turbulent, and in between this is transitional. Clear?
Yes, sir.
That means the HF velocity plot behaves differently in laminar zone and in turbulent zone. Okay, and if you go beyond C, then it may take the form like this or this or this, based on the roughness of the wall of this pipe. Okay, clear, guys?
Yes, sir.
Yes, sir.
If the surface n, if the surface is very rough, then the value of n will be, let's say, 2, and if the surface is smooth, then n might be 1. Okay, smooth wall pipe, if it's smooth, then it will be 1.75. Okay, as you can see, this graph is for n equals to 2, this might be for n equals to 1.75, and so on. If you look at this, that when n equals to 2, that means the wall is rough, so the head loss is higher. And we can see, yes, that in this line the head loss is higher than this line, right? Because this is above than this line. Am I right? For a particular velocity here, which one has higher head loss? This one, right? Than this one.
Two, higher.
This one is higher, right? N equals to 2 is
Yes, sir.
higher. Why? Because roughness, this is rough, or rough wall. So as the surface is rough, so the frictional head loss will also be higher. There will be more loss of energy. That's why. So now the question is, um, I already told you these things. So eventually, what we found here, that HF is proportional to V to the power n here. HF, head loss Y, and this is X. This is Y, this is X. This point B is called the critical point. Why? Because here the um, higher critical point, because here the curve starts changing its characteristics, and A is the lower critical point. B is the higher critical point here. B is the higher critical point, and A is the lower critical point. Okay. The question is, velocity is not the only factor that determines whether the flow will be laminar or turbulent. So velocity is not the only factor which determines whether a flow will be a laminar or turbulent. So what are the factors? We can understand this based on Reynolds number, which is Re is equals to V into D over nu, where nu is the kinematic viscosity, which can be expressed as dynamic viscosity divided by rho. Mu is the dynamic viscosity, and mu is the kinematic viscosity. So kinematic viscosity equals to dynamic viscosity divided by rho. So if you take kinematic viscosity, then Reynolds number equals to V into D over nu, where V is the velocity of the pipe, velocity of the water through the pipe or fluid through the pipe. This is V, and D is the diameter of the pipe. Are you following me, guys?
Yes,
Yes,
sir.
sir.
So as you can see, this Reynolds number depends on V, velocity D, that means the diameter, as well as the nu, that means this is the viscous property of the liquid. Now, if this, by the way, this Reynolds number is a dimensionless number, it doesn't have any dimension. That means if all the dimension has been cancelled in the numerator and denominator. Now, if Reynolds number is less than 2000, that means the flow is laminar. If the Reynolds number is greater than 4000, that means the flow is turbulent in circular pipes. In circular pipes. Did I make it clear?
Yes,
Yes.
sir.
So if there is a pipe flow, and if I give you the velocity and give you the diameter, and if I tell you the name of the fluid or viscosity, then, and if I ask you, now tell me whether the flow is laminar or turbulent, what would you do? The question is whether the flow is laminar or turbulent. What would you do?
We calculate the Reynolds number.
Reynolds number, and then see whether the value is less than 2000. This is laminar. Whether the value is greater than 4000.
Turbulent.
This is turbulent. And in between 2000 to 4000, that will be transitional. That will be transitional. Okay. Any question?
No, sir.
Okay. So if you go to the back at the end of your book, Franzini, you'll find the value of viscosity of water at different temperature, because this changes with temperature. You'll get this value. Here you can get an idea. Dynamic viscosity. That means mu, and kinematic viscosity, that is mu, different temperature. Now the question is, we are telling this value, the 2000, 4000, this is for circular pipes. Now what if you have a rectangular pipe or any other shapes of pipe? In those cases, how do you get this diameter? How do you get this diameter? Which diameter? This diameter, right? D or capital D, right?
Yes, sir.
In those cases, we can get a hypothetical radius that is called hydraulic radius, which is defined as cross-sectional area divided by weighted perimeter. A is the cross-sectional area of the flowing fluid, and P is the weighted perimeter. That is called a hydraulic radius. That means RH will be, let's say the water is here, water level is here, then this is the cross-sectional area, A by cross-sectional area divided by P. What is P? P is the weighted perimeter. Weighted perimeter means only the portion which is weighted. And weighted means only the weighted perimeter means only the perimeter which is weighted. That means water existing. That is only this parameter. Weighted perimeter. Clear, guys? Clear?
Yes, sir.
This is P. So by this way, you can calculate the Reynolds number. So sorry, this is not Reynolds number. This is hydraulic radius. This is hydraulic radius. So in this way, you can calculate the hydraulic radius, hypothetical hydraulic radius for non-circular as well as circular pipes. If it's a circular pipe, then RH is what, guys? A divided by P, right? Hmm? Right?
Yes, sir.
If this is if the diameter is small r, then A equals to what?
I by 4 D square, sir.
Pi by 4 d square or pi r square, right? And
Yes, sir.
P is what? Twice pi r, right?
Yes, sir.
Is twice pi r, and this is pi r square. So if you cancel this out, and it will be r by 2, am I right?
Yes.
Yes.
Or it will be, if you express this in terms of d diameter, then it will be d by 4, because r equals to d by 2. R equals to d by 2, so d by 4. So for circular pipe flowing full, it has to be flowing full. For circular pipe flowing full, hydraulic radius equals to d by 4. Any question?
No, sir.
For full pipe flow, this is d by 4 hydraulic radius. If the flow is not full, like the flow is here, then it may not be it is not d by 4. It is something else, because in that case you have to take this cross sectional area instead of the complete cross sectional area. Okay,
Yes, sir.
fine. Friction head loss in conduits of constant cross section. This discussion applies to either laminar or turbulent flow and to any shape of cross section. That means it can be applied to almost all of the conditions. So this is a general kind of derivation or expression. What's happening here? Look at this. This is a pipe, and here there is a flow of fluid in this direction. Okay, this is the datum. If maybe you are using a pump to lift the water to the pipe. Okay, this is the point 1, this is point 2. Okay, this is the static head plus this is the static head. Z1, this is Z1 plus P1 by gamma. This is P1 by gamma. Are you following me, guys?
Yes, sir.
Yes, sir.
And for this point, this is Z2, and then this is P2 by gamma. So this is the static head here. So if you connect these two lines, you will get hydraulic head line. Similarly, this is V square by 2G, this is V square by 2G. So if you add this, you'll get the energy line here, you'll get the energy line here. If you connect these 2 points, it will be energy line. So the total energy here is up here, and the total energy at this point 2 is this. So the difference among these two value is the head loss, HF, right?
Yes, sir.
Okay. Now, if you take the free body diagram of this fluid part, I'm talking about the fluid part, not the pipe, the fluid inside the pipe, then what would you see? You'll see there is friction between the pipe wall and the water. So these are the shear stress, right? Which has been generated due to the friction between the wall of the pipe and the water. Okay,
Yes, sir.
fine. And from this side, I mean, this friction will act surrounding the pipe everywhere. Okay, everywhere. This is the pressure. This is the pressure. Since we are taking the free body diagram, so the direction will be towards the fluid mass. If this is the angle theta, then this should also be theta or alpha, whatever you say. And there is also the weight of the mass of the fluid working, acting downward. This is the length of the pipe, and this is the length of the fluid mass that we are considering here. Any question, guys?
No, sir.
Now, this is the stress. Remember, this is what? This is the stress. This is stress. So this stress is acting on this surface, right?
Yes, sir.
If you multiply this shear stress with this surface, you'll get what? The force, am I right? Huh?
Yes, sir.
Yes.
Yes, sir.
So multiply which area with which area? This is not cross-sectional area. This is not this cross-sectional area. This is the surface area here, the body, right? A surface, let's say AS. What is this value, guys? The surface area is what? The surface area is perimeter twice by R multiplied by L, right? Are you following me? This L multiplied by is twice by
Yes,
R.
sir.
Then you'll get the surface area. So stress into AS. This is what? P, that means perimeter into L. Perimeter into L. This is the force. Clear? Average
Yes.
stress. This is the average shear stress. Because shear stress varies. Shear stress varies in this profile. So we are taking the average shear stress. And if this is the weight acting downward, weight is what? Weight is unit weight gamma multiplied by volume. Volume is cross-sectional area multiplied by length. So gamma into volume. This is gamma into volume. Volume is cross-sectional area multiplied by L. Cross-sectional area multiplied by L. That's the volume, right?
Yes, sir.
Gamma equals to what? Weight per unit volume. Weight per unit volume multiplied again this volume. So this cancels out. This is W. This is W. Okay. So W equals to gamma AL. We can write that, right?
Yes, sir.
Now, if this is alpha, this is what? 90 minus alpha, right?
Yes, sir.
This is alpha and this is 90. This is 90 minus alpha. Let's say this is alpha then. Opposite triangle. This is alpha, this is alpha. And this is 90 minus alpha. Alright? This is alpha. This part is alpha. Let me use a different color, maybe This one. So this is alpha. Hmm. And this is 90 minus alpha. Any question?
No,
Any
sir.
question? Okay. Now this is alpha in this one. So the component in this direction will be what? W into cos alpha, right? Hmm?
Ji, sir.
So this is W, this is alpha, this is W cos alpha, and perpendicular to this is W sin alpha. Similarly, this is W, this is alpha. So in this direction, it will be W cos alpha, and in this direction, it will be W sin alpha. Okay, and W equals to gamma AL. We just derived it. Clear?
Yes, sir.
Okay. And now if you um, do this summation of F equals to 0, because this is equilibrium in a steady flow, the summation of forces acting on any fluid element must be equal to 0. So here this is equals to 0. This is why, what is the average shear stress? Look, if this is the pipe, the shear stress varies. Here the shear stress is maximum. Why? Because the wall pipe is existing here. So shear stress will be maximum here. As you go towards the center, shear stress will be minimum. And again, as you go towards the wall pipe, the shear stress will increase. This is the shear stress diagram. Clear?
Ji, sir.
Now, if you look at the velocity diagram, here the velocity is minimum. So the shear stress is minimum. So velocity will be maximum. Here, the shear stress is maximum. So the velocity will be minimum. So the flow will be like this. Velocity profile. This is the velocity profile, and this is the shear stress profile, right? Right.
Ji, sir.
And you can see this shear stress varies through the depth of the pipe. And now if you want to take the average kind of shear stress, the shear stress is 0 to P, tau 0 dP divided by P, according to the perimeter. So if you just rearrange those and replace these values, finally you'll get this HF, head loss. Look, we are getting what? Head loss. Head loss equals to average shear stress multiplied by the length of the pipe divided by RH into gamma, where RH is what, guys? Hydraulic radius. Remember, A by P. Okay, clear?
Yes, sir.
So why did we perform this derivation, guys? To calculate the head loss. Because let's say if you want to design a pipe network, you want to supply water, let's say Dhaka, they want to supply water from source to the community. Now you need to design this pipe. What will be the diameter of this pipe, right? What will be the slope and these things? Now, if you want to do this, as the water flows from here to there, there is frictional head loss, am I right? And other head losses, right?
Yes,
Right.
sir.
So you need to know this frictional head loss. Otherwise, how would you design? You have to give this extra energy from here. Let's say you need 100 here at this point, right? And your head loss is 10. So if you provide here at the source energy, it's 100. So by the time the water reaches here, how much you will get? 100 minus this 10. You'll get 90. But your requirement is 100. Is the design sufficient?
No, sir.
So you need to provide what? You need to provide 110. And then you'll get 100 here. 110 minus 10 equals to 100. That's why you need to know this. We are trying to identify this. Okay. Any question?
No, sir.
Now, this equation is applicable to any shape of uniform cross section, regardless of whether the flow is laminar or turbulent. So it can be applied to laminar flow, turbulent flow, circular cross section, rectangular cross section, or any other shapes. But if you look at this equation, you'll see that we have shear stress here, and it's difficult to identify the shear stress. So here, the engineers are smart. They've applied dimensional analysis. Dimensional analysis means here we analyze based on some entities which does not have any dimension. Okay, and then we have replaced these HF with another value, that is CF. What is the relationship between HF and CF? This is the relationship. This is the relationship. Okay. Now, what is HF by L? Let's say I'll go back to the previous figure that we discussed. It will be easier for you. So look at this figure. Look at this triangle. Let's draw this. This is the pipe. Let's say this is the flow direction. This is total energy 1, total energy 2. So the elevation difference here, this is head loss HF. So this and this. So if you look at this triangle, This, let's say this is L. So what is the slope, guys, for this angle theta equals to, if I tell you this is tan theta equals to what? This height divided by base, am I right? For this triangle.
Yes, sir.
So height is HF and base is L. So this is actually the slope S. So that's why they are denoting this as slope. An expression for the slope of the energy line. So this is the energy line. HF by L. This is the energy line, and this is the slope. This is the slope of the energy line, which is S equals to tan theta equals to HF by L. Okay, clear, guys?
Yes, sir.
So this is the expression. Now, if it's a circular pipe flowing full, then we know that RH equals to D by 4. We just derived it, right? In the earlier today, right? RH equals to D by 4 or R by 2, remember?
Yes, sir.
Now, substituting this value in equations 8.11, these, and 8.12, we obtain for both smooth wall and rough the well-known equation for pipe frictional head. So this equation 8.11 and 8.12, I have just repeated this 8.11 and 8.12 here. If you put this value here, okay, and if you replace these values, you'll get head loss equals to F into L by D V square by 2G. Okay, clear?
Yes, sir.
Now remember, this expression is for only circular pipe flowing full. So this expression is also for circular pipe flowing full, either laminar or turbulent flow. But it has to be circular pipe flowing full. So then you can write HF equals to F into L by D V square by 2G. So did you see one thing, that previously in this equation we had this, right? Then we replaced that shear stress with a factor. Did you see here? This shear stress has been replaced with a factor. Did you see? And with other terms. Did you notice it, guys? Can you hear me?
Yes, sir.
Yes, sir.
So this is HF,
Sure.
this is also HF. So we have replaced this shear stress with a factor. Did you see this?
Yes, sir.
Sir.
Why? Because this is difficult to determine. So we have replaced it with a factor. Okay, so we are making it easier so that we can calculate it. And we have further replaced this CF with the friction factor that is called F. Okay, what is the relationship between F and CF? This is the relationship. Okay, so this is the friction factor. Finally, the shear stress has been replaced with this. But you have to remember that this equation is for circular pipe only flowing full. And this is a very famous equation. This is called Darcy-Weisbach equation. Darcy-Weisbach equation. And like the coefficient CF, the friction factor F, also sometimes called the Darcy friction factor, is dimensionless. Okay, this is also dimensionless. Clear, guys? Is it clear?
Yes, sir. Yes, sir.
Friction in circular conduits, so we can write this circular pipe flowing full, you can I already discussed this, that the shear stress changes and then the velocity distribution. Shear stress is the minimum, but here velocity is the, therefore the velocity here is the maximum. Now if it's a non-circular conduit, then you cannot write RH equal to D by 4. For a circular conduit you can write this, but for a non-circular conduit you cannot write this. Now for non-circular conduits, what would you do? How do you calculate D? How do you calculate D for non-circular conduits? For non-circular conduits, this is for circular conduits, right? So from
Yes, sir.
here you can write D equals to 4 into RH. So if you replace this value D as 4 into RH, then you have the hydraulic radius instead of D. So now for non-circular conduits you can calculate RH as A by P. This is kind of approximation. Okay, RH equals to A by P. RH and R is different thing. This is Reynolds number, by the way, and this is hydraulic radius. Reynolds number equals to V into D over nu. Now, this approach gives reasonably accurate results for turbulent flow. However, the results are poor for laminar flow because in such flow, viscous action causes frictional phenomena throughout the body of the fluid. So what we have tried here, that okay, we know that for circular pipe flowing full, this is the equation. Now the question is, what is for non-circular pipe? Then what have you done? We have replaced this D with 4 into RH and we got this. So for non-circular pipes also, you can calculate RH as A by B and you can put this value here, you will get the value of HF. But this approximation does not work well in case of laminar flow. Why? Because if you look at the laminar flow, in case of laminar flow, the viscous action causes frictional phenomena throughout the body of the fluid. That means you have the viscosity here, here. The frictional force acting throughout the body, okay? Clear? This is laminar flow. But in case of turbulent flow, what is happening? In case of turbulent flow, we know that the viscous force is not the dominating here. The inertia force is dominating here. So what's happening that in turbulent flow, a layer of laminar flow is formed near the wall of the pipe. Near the wall of the pipe, this is laminar, but here this is turbulent. Okay? Are you following me, guys?
Yes, sir.
Yes, sir.
Why? Because the reason is, when you are moving at 5 meters per second and you strike an object versus when you move at 50 meters per second and you strike an object, you will get hurt. In this case, with a greater intensity, am I right?
Yes, sir.
You'll be hit with the greater intensity here. So here in turbulent flow, your velocity is much higher. Let's say this is 50, this is 5. So, and you have the frictional surface here, I mean rough surface here, pipe wall. So here, due to the high velocity overall and friction, this layer which is close to the pipe wall, they cannot move faster. So there is a slow moving layer, but here is a fast moving layer. There is a slow moving layer, and this layer therefore is a laminar flow layer. So in case of turbulent flow, the laminar layer exists only near the wall, but in laminar flow, the laminar flow occurs throughout the body of the fluid. But here, no, not throughout the body, only here and here. Here, this is turbulent flow. Okay? In turbulent flow, the frictional effect occurs largely in the region close to the wall. As I told you, close to the wall. Only here, this is the laminar flow region. This. Okay? It depends on the weighted perimeter. That means it depends on the weighted perimeter. And therefore, accurate results can be obtained. So here, this depends on the weighted perimeter, because this is near the wall of the pipe. That's why here, this kind of conversion acts well in case of turbulent flow. But in laminar flow, this acts throughout the body. So it is not directly dependent on the perimeter. It depends on the perimeter. So it doesn't work well in laminar flow. Did I make it clear?
Yes, sir.
So for laminar flow, we have another derivation which is like this. HF. Yeah, here. If you convert this, yes, this one I was talking about. So for laminar flow, this is the equation. HF equals to this. Previously, this was what? HF equals to F into LYD V square by 2G. This is for turbulent flow, right? This is for turbulent flow, and this is for laminar flow. Clear?
Yes, sir.
Yes, sir.
Remember, as a civil engineer, we design pipes and hydraulic structures. In 90% cases, we will get turbulent flow. Laminar flow is very small, very slow moving liquid, and we don't usually get them. Sometimes, majority of the time we get turbulent flow. Clear? Sometimes we get laminar flow. This is the turbulent flow formula, head loss, and this is the laminar flow formula for head loss. And this is called Hagen-Poiseuille law for laminar flow in tubes. Okay. So this is for laminar, this is for turbulent. If you compare these two equations, this one and this one, you will see that F is 64 divided by R, where R is the Reynolds number. Any question, please?
No, sir.
Entrance condition in laminar flow. Okay,
Today I will discuss on our previous lectures how to get prepared for your meet. So that's the end of the lecture. Thank you very much. Have a good one and stay safe.